Black holes, pretty incredible, right? I mean, just huge things in space so dense, not even light can escape.
That's right.
What if I told you they might hold secrets to, like, the fabric of the universe itself?
I like that. Secrets.
Today, we're diving deep into an article from The Conversation called Guardians of the Universe: How Quantum Black Holes Hide the End of Space and Time.
Catchy title.
Right. And it was written by a whole team of physicists. It explores some wild ideas about what happens at the edge of reality.
Oh, yeah, definitely.
So we're going to unpack some pretty heavy concepts, like singularities, cosmic censorship, and how quantum mechanics just throws a wrench into everything we thought we knew.
You said edge of reality before, and that's really what we're talking about with singularity.
Okay. So singularities, what are they? Why should we care about them?
Well, in the simplest terms, a singularity is a point in space where the curvature of space-time becomes infinite.
So like all the matter of a star compressed into a single point?
Exactly. And at a singularity, gravity becomes infinitely strong, and all the laws of physics as we know them, they just break down.
It's like the universe's divide by zero error.
That's a great analogy.
Right.
And you can see why this presents a problem for us physicists.
Yeah.
If singularities were observable, if they were just out there for us to see, it would mean that our ability to predict anything with certainty, would completely disappear.
Whoa.
Cause and effect would go out the window.
Chaos. But didn't Einstein's theory of general relativity, does that predict that these singularities have to exist?
You're absolutely right. Einstein's theory, which has been incredibly successful at describing gravity, it leads us to these points of infinite density in certain situations, like the collapse of a massive star. One of the authors of the article, Roger Penrose, he actually proved mathematically that singularities are inevitable.
Wow. So they have to be there.
Under certain conditions, yeah.
Okay. So we've got these physics-breaking singularities that we know are probably out there. So how does the universe protect itself from this?
Good question.
That's where the idea of cosmic censorship comes in, right?
Precisely. The cosmic censorship conjecture, it was proposed by Penrose himself. It essentially says that nature is shy about its singularities.
Okay.
It suggests that these points of infinite density are always clothed by something that prevents us from directly observing them.
I like that. Clothed. So what's the universe's clothing of choice?
Black holes.
Okay, so black holes are acting as cosmic sensors, hiding the singularities from the rest of the universe.
Exactly.
But how does that actually work?
Well, a black hole is a region of space-time where gravity is so strong that nothing, not even light, can escape.
Right.
This point of no return is called the event horizon. The singularity, it sits at the center of the black hole, hidden behind this event horizon.
Okay.
So while the singularity might be lurking in there, we can't actually see it or interact with it directly.
So it's effectively censored?
Censored from the rest of the universe.
Right. I see. Black holes. Out of sight, out of mind.
But you said this is a conjecture, right? Not a proven fact.
That's right. It's been a major puzzle for physicists for over 50 years now. It's one of the biggest outstanding questions in our understanding of gravity.
Wow. So we've got these singularities that probably exist, but they're hidden away behind the event horizons of black holes. Seems like a pretty tidy solution, but I have a feeling we're just scratching the surface here, because we haven't even talked about the quantum world yet.
You're reading my mind. This is where things get really interesting, because when we introduce the world of quantum mechanics, it throws a whole new set of challenges and possibilities into the mix. It's a whole other ball game when we start talking about quantum black holes. You see, quantum mechanics and general relativity don't always play nicely together.
How do we even begin to understand what's happening at that level?
Physicists are working on a complete theory of quantum gravity, but we're not quite there yet.
Oh, okay.
However, there are approaches like semi-classical gravity.
Semi-classical gravity, what's that? It's like dipping our toes into the quantum pool without taking the full plunge.
I like that.
We treat space-time as described by general relativity, but we allow matter to be described by quantum mechanics.
Interesting. So what if we learn? Does quantum mechanics make the whole singularity problem better, or does it just add more problems?
A bit of both, actually. On the one hand, a complete theory of quantum gravity should resolve the problem of singularities altogether.
Wait, so singularities would just disappear?
Not necessarily disappear, but their infinite nature would likely be smeared out somehow, smoothed over by quantum effects.
Okay, that makes sense. But then why are we still worried about cosmic censorship if quantum gravity is going to save the day?
Because, and here's where things get really tricky, quantum mechanics introduces some new wrinkles that could potentially violate the assumptions of Penrose's original singularity theorem.
Like what?
Well, one of the key assumptions of that theorem is that matter always has positive energy.
Yeah, that makes sense.
That's the classical intuition. But the quantum world doesn't always play by the rules.
Oh, here we go.
Quantum mechanics allows for something truly bizarre. Negative energy.
Negative energy. Less than zero. How is that even possible?
Sounds crazy, but it's a real phenomenon.
Oh.
There are things like the Casimir effect, where empty space itself can have negative energy fluctuations.
You know, that's wild.
And if negative energy is possible, it could potentially mess with the whole singularities are always hidden idea.
Oh, so quantum mechanics gives with one hand and takes away with the other.
It's a delicate balance.
Is there any evidence to suggest that these naked singularities might actually exist?
That's the big question. The truth is, we don't know for sure. But there has been some fascinating research suggesting that quantum effects might actually strengthen the idea of cosmic censorship.
Really? How could quantum mechanics make cosmic censorship even stronger?
It does seem counterintuitive, but remember how we talked about quantum dressing of singularities?
Yeah, like giving them a quantum disguise.
Exactly. The article mentions some work done by physicists Roberto Imperan, Alessandro Fabri, and Nemanja Kaliper back in 2002. They showed that in certain quantum scenarios, singularities could be modified by quantum effects in a way that actually shields them from view.
So the singularity is still there, but quantum mechanics is like, nope, you can't see this.
That's one way to visualize it. And what's even more interesting is that this quantum dressing seems to be a common feature of all the known examples of quantum black holes.
So maybe quantum mechanics isn't working against cosmic censorship after all. Maybe they're actually on the same team. But how can we be sure? Is there any way to test this idea of quantum cosmic censorship?
There's a fascinating concept known as the Penrose inequality that provides a potential way to test this idea.
The Penrose inequality. Lay it on me.
It's a mathematical relationship that connects the mass or energy of space-time to the area of black hole horizons.
So more mass, bigger black hole, bigger event horizon.
Exactly.
Yeah.
But the Penrose inequality goes beyond intuition. It makes a specific quantitative prediction about this relationship. And here's the key. If the Penrose inequality holds true, it strongly supports the idea of cosmic censorship.
I'm not sure I follow.
Because if you could somehow violate the Penrose inequality, it would strongly suggest that you might also be able to have a naked singularity.
Okay, so the Penrose inequality is like a cosmic safeguard.
That's the idea. And this is where things get really exciting, because the authors of our article have been working on something called the quantum Penrose inequality.
A quantum version.
Precisely. The quantum Penrose inequality takes the original concept and extends it to the realm of quantum mechanics. It incorporates the entropy or disorder, not just of black holes, but also of quantum matter.
Entropy. So we're throwing thermodynamics into the mix now.
It all connects. The quantum Penrose inequality essentially says that the total entropy of a region of spacetime, including the entropy of black holes and quantum matter, has to be greater than or equal to a certain value that's determined by the mass or energy of that spacetime.
So there's a limit to how much entropy you can pack into a given space.
Right. And if you exceed that limit, it suggests that you might be able to violate cosmic censorship.
So the quantum Penrose inequality is like a quantum cosmic censor, keeping everything in check.
That's a fantastic way to put it. And what's really exciting is that the authors of this article have found a version of the quantum Penrose inequality that seems to work for all the known examples of quantum black holes, even when quantum effects are strong.
Wow, that sounds like a pretty big deal. Does this mean they've proven quantum cosmic censorship? Proven? Not necessarily, but it's definitely evidence in favor of it.
It seems like even in the crazy world of quantum mechanics, those singularities might still be safely tucked away, hidden from view.
Okay. I'm still a little fuzzy on how entropy fits into all of this, though. I remember it from high school physics as something about disorder, but how does that relate to black holes and this quantum Penrose inequality?
Yeah. Entropy can be thought of as a measure of how spread out energy is within a system.
Right.
More entropy means more disorder, more possible ways for that energy to be arranged. And the second law of thermodynamics, you remember that?
Vaguely.
It tells us that the total entropy of a closed system can never decrease over time. like our universe.
Got it. So everything is always moving towards a state of more messiness.
Right. And what's fascinating is this quantum Penrose inequality. It links that tendency towards disorder with the very structure of space-time itself.
Wow.
It sets a limit on how much entropy can be packed into a given region of space-time.
So if we try to cram too much entropy into a region of space-time, it's like we're trying to force the universe to become more ordered than it's allowed to be.
Yeah. That's a great way to think about it. And the consequence of trying to violate this entropy bound or trying to create too much order in one place is that you might end up with a naked singularity.
A singularity not covered up.
Exactly. Because a naked singularity would be like the ultimate form of order, wouldn't it? All that mass and energy concentrated into a single point.
And that would violate the second law.
Right. It would be a violation of the universe's natural tendency towards disorder, towards increasing entropy. And that's why the second law of thermodynamics might be one of the deepest reasons why cosmic censorship holds true.
It's like the universe itself is enforcing this rule.
The cosmic dress code, to make sure that those singularities stay properly covered up.
That is a really mind-blowing idea. So while there's still so much that we don't know about black holes, singularities, and the quantum nature of gravity, it seems like the universe might have its own set of safeguards in place to keep things from getting too out of control.
It's incredible.
Yeah.
From Einstein's theory of general relativity to the world of quantum mechanics and the laws of thermodynamics, it's like we're catching glimpses of a deeper order underlying the universe.
This deep dive has been a wild ride. We've explored some of the most fundamental questions about the nature of reality. And while we might not have all the answers, we've learned a lot.
It's a reminder that there's always more to discover.
Absolutely. So we'll leave our listeners with one final thought to ponder. If we could somehow observe a naked singularity, if that cosmic dress code were violated, what would it look like? What would it tell us about the universe?
Now, that's a question worth thinking about.
It sure is. Thanks for joining us on this deep dive into some of the universe's biggest mysteries. We'll see you next time.